Hi, I will now discuss to you the different types of collision. Now when objects collide, many things can happen depending on the characteristic of the colliding objects. Now the momentum is conserved in a closed system. Let's differentiate the collision of two bouncy balls and the collision of two lumps of clay. Now for the balls, they will just bounce off of each other. But for the clay, if they collide, they stick together and in essence become one object. Now for the bouncy balls, their collision is an example of elastic collision. Take this plastic egg for example. When it hits the wall, it bounces off and retains its original form. Now in this video, you will see a cue ball hitting billiard balls. Here you will see a cue ball hitting the Uno ball. And here you see the cue ball hitting the same Uno ball, now making a 90 degrees angle. Now according to the conservation of linear momentum, the equation for elastic collision of two objects is m1 v1 plus m2 v2 equal to m1 u1 plus m2 u2. Now to understand this, take this ball for example, with mass 1 going in the positive x direction with velocity 1, colliding with another ball with mass m2 going in the negative x direction with velocity v2. Take note the direction of ball 2 going in the negative x direction, meaning the value for its velocity should be negative. Now the product of this is the momentum of the first ball and this is the momentum of the second ball. The sum of their momentum should be equal to the sum of the momentum after the collision. Now after the collision, ball 2 goes now in the negative x direction, still with mass 1, but now with velocity u1. But now it's going in the negative x direction, the value for u1 should be negative. Now for the second ball goes now in the positive x direction, still with mass 2, but now with velocity u2. That is how we came up with this equation. Now what if still the same ball now colliding with a ball at rest with mass 2, but because it is at rest, the velocity is equal to 0. In this case, if the velocity is 0, you will just cancel this out, making now the equation m1 v1 equal to m1 u1 plus m2 u2 is equal as that. Let's now move on to the second type of collision, which is inelastic collision. An example of this are two lumps of clay colliding with each other, sticking together and in essence becomes one object. Or clay hitting a wall, sticking into it and deforming. Just like that. The clay sticks to the wall and the clay becomes deformed. Now, the equation for an elastic collision is m1 v1 plus m2 v2 equal to quantity m1 plus m2 u1. Now to understand this, take this ball of clay for example with mass 1 going in the positive x direction with velocity v1 colliding with another lump of clay mass 2 and v2. Now instead of bouncing off of each other, they collide, stick together and became one object. Let's say when it goes to the positive x direction. And because they stick together, their mass should be the sum of m1 and m2. And now because it is just now one object, they have the same velocity, which is a u1. There are actually three types of collision: elastic collision, completely inelastic collision, and partially inelastic collision. Now this is the equation for a completely inelastic collision. Now for the partially inelastic collision, its equation is the same as the equation for the elastic collision. The only difference is for the partially inelastic collision, just like elastic collision, they separate after collision, but the colliding objects are now deformed.
So in this video, I'm going to show which of these two batteries with different mass and radius is going to reach the bottom of the inclined plane first. As what you have seen in the video, both batteries reach the bottom of the inclined plane at the same time. It is because radius, length, and mass doesn't matter as long as they are the same type of solid.
Hi, I would like to explain the principle behind measuring gravity with a pendulum. If we suspend a mass at the end part of the string, we have a simple pendulum. Pendulums have been around for thousands of years. Ancient Chinese used a pendulum to help predict earthquakes, and Galileo Galilei really studied the principle of pendulum and lead to the first clock. Pendulum is a simple tool that can also determine gravity. By theory, the period of oscillation of a pendulum is inversely proportional to the square root of the acceleration due to gravity. Or by formula, period is equal to 2 pi times the quantity square root, the length of the string, over gravity. By theory, the acceleration due to gravity at sea level is greater than the acceleration due to gravity at a certain altitude, and by this experiment we will prove that theory.
Hi, we are now in Makati Executive Tower 2, ground floor, and we are about to perform determining gravity using simple pendulum.
Hi, I'm going to show you the solution determining the gravitational pull using simple pendulum. The formula for the gravitational pull using simple pendulum is frequency is equal to 1 over 2 pi times square root of the known gravitational pull over the length of string. Given that the length of string in the experiment is equal to 0.3 meters, the frequency at the top of the building equal to 10 cycles per 11.4 seconds, and frequency at the bottom or the ground floor equal to 10 cycles over 11.1 seconds. Solving for the gravitational pull at the top of the building, we substitute the frequency at the top to the formula. Frequency at the top is equal to 10 cycles over 11.4 seconds equal to 1 over 2 pi times square root of a known gravitational pull over the length of string, which is 0.3 meters. And using the shift zone function of the calculator, we obtain the gravitational pull at the top of the building, G top, equal to 9.11 meter per second. Finding the gravitational pull at the ground floor of the building, we substitute the frequency We substitute this frequency at the bottom of the formula. Frequency at the bottom is equals to 10 over 11.1 seconds, 10 cycles over 11.1 seconds is equal to 1 over 2 pi times square root of the unknown gravitational pull at the ground floor over 0.3 meters, which is the length of the street. And using again the Ship-Solved function, we obtain the gravitational pull at the bottom or the ground floor equals to 9.61 meters per second squared. In this experiment, we can conclude that as far as we go beyond the surface of the Earth, which is the sea level, we experience less gravity, far from the original value, which is 9.8, far or close to the original value, which is 9.8 meters per second squared.